The chilling vacuum of space, that infinite expanse we so often romanticize with glittering diamond dust scattered across black velvet, is, upon closer inspection, a roiling crucible of cosmic violence, a theater where catastrophic collisions are not the exception but the rule. Imagine, if you will, standing upon the scarred, desolate plains of a world orbiting a star light-years from Sol, where the nocturnal canvas is not the familiar pinpricks of distant suns but a churning, incandescent storm of pulverized rock and superheated gas, the residual fallout from titanic impacts that have recently reshaped that alien solar system. The imagined thunder of these colossal smashes, reverberating through the tenuous atmosphere, feels like the very heartbeat of the universe accelerated by existential dread, a raw testament to the boundless, indifferent power that governs celestial mechanics. Does such a place exist, a world capable of maneuvering itself, of executing a cosmic sidestep to evade the fate of being torn asunder by gravitational shear or outright planetary battering? This question haunts the minds of astrophysicists and space enthusiasts alike, for the cosmos is anything but the serene clockwork mechanism Newton once envisioned. It is a dynamic, often brutal arena riddled with existential threats, from the lonely drift of rogue worlds to the cataclysmic encounters that can rewrite the history of an entire stellar nursery. Let us embark on an extended voyage through the current frontiers of exoplanetary science and celestial dynamics to illuminate these secrets, weaving the latest data and hypotheses into a continuous, compelling narrative tapestry. To truly grasp the precariousness of planetary existence, we must first contextualize our own neighborhood. Our solar system, with its 8 tidy planets tracing relatively stable elliptical paths around the Sun, appears paragons of order. Yet, this stability is hard-won. Billions of years ago, during the tumultuous infancy of the Sun, the nascent planetary orbits were anything but fixed. They danced chaotically within the vast protoplanetary disk, a swirling accretion of gas and dust, where collisions were not rare events but standard developmental hurdles. The most celebrated, and indeed formative, terrestrial catastrophe remains the hypothesized impact between the proto-Earth and Theia, an Mars-sized protoplanet. Approximately 4,500,000,000 years ago, this monumental collision was not a glancing blow but a nearly head-on collision, unleashing an energy surge so immense it vaporized much of Earth's crust, stripping away its nascent atmosphere in a fiery ejection. From that incandescent shroud of vaporized rock and molten debris, our moon coalesced, a faithful sentinel whose stable gravitational presence regulates Earth's axial tilt, a crucial factor underpinning the long-term climatic stability necessary for the evolution of complex life. Furthermore, recent analyses, such as those presented by researchers at the University of Bern in 2023, bolster the increasingly accepted theory that water and other volatiles, the very ingredients for life, were likely delivered to Earth through such violent accretionary processes, bombarded in from the outer reaches of the system or even captured from interstellar space via these energetic early interactions. But moving beyond this retrospective view of our violent genesis, can a planet actively dodge such lethal encounters? While planets obviously lack consciousness to plot an escape route, the mechanisms governing their movement often result in de facto evasive maneuvers, evolutionary adaptations to gravitational turbulence. A core concept here is planetary migration, the large-scale shifting of planetary orbits during the stellar formation epoch. Giant gas planets, analogous to Jupiter, can spiral inward toward their host star as they interact gravitationally and hydrodynamically with the remaining circumstellar gas and dust disk. Envision Jupiter, an immense entity of swirling vortices and unimaginable mass, effectively plowing through the disk, its gravity either flinging smaller bodies outward into the deep cold or, in some cases, sweeping them into its own gravitational maw. Data compiled by NASA over years of modeling suggests that in our own system, Jupiter executed a complex inward then outward migration, the so-called Grand Tack Hypothesis, which proved fortuitous. This movement may have cleared out a significant population of planetesimals and comets that would have otherwise subjected the inner solar system, including Earth, to a continuous, sterilizing barrage. Without this timely, albeit mechanical, migration, life's emergence would have been profoundly hindered. Compounding this understanding, observations in 2023 revealed the spectacular collision of 2 gas giants in a distant stellar system, an event that momentarily bloomed into a massive, donut-shaped dust cloud, a potential birthplace for new planets or moons. This spectacular finding underscores the dual nature of cosmic impact. It is both the ultimate destructive force and, counterintuitively, a driver of planetary evolution. To survive, however, a world must navigate this transitionary phase, effectively shifting its position at the critical juncture. Consider next the ultimate form of planetary escape, the rogue planets, or interstellar nomads. These are worlds that have been violently ejected from their natal systems, cast adrift into the cold, lightless expanse between the stars. In a morbid sense, these planets have successfully avoided immediate annihilation by escaping the gravitational anarchy of a crowded system, trading close-range violence for eternal solitude. They are flung outward through intense gravitational perturbations, perhaps when a stellar binary pair passed too closely, or when a massive planet gravitationally bullied its smaller siblings off their orbits. Picture such a world, eternally dark, shielded from solar warmth, its surface a landscape frozen under kilometers of inert ice, winds howling silently across jagged, airless mountains. Estimates, highlighted in news reports from sources like Newsweek in 2023, suggest that rogue planets might vastly outnumber the stars in the Milky Way galaxy, a staggering population hidden in the dark. While their sheer number makes close encounters theoretically possible, the probability of a rogue planet striking Earth remains infinitesimally small, given the enormous interstellar separation. Yet, escaping the central system means trading one danger for another. They become subject to higher rates of impact from stray asteroids and comets in the sparsely populated interstellar medium, lacking the systemic shepherd bodies like Jupiter to clear their path. A fascinating query raised on world-building forums often ponders if rogue planets encounter more debris. The consensus, based on orbital dynamics, leans toward yes, as their trajectories are inherently unstable across galactic scales compared to planets bound by a central star. Nevertheless, some of these wanderers may harbor a secret to longevity: deep subterranean oceans warmed by residual geothermal energy or radioactive decay within the core, providing a haven for microbial life to persist through eons of cold transit. To illustrate a more subtle, yet crucial, form of successful orbital maneuvering within a stable system, we turn to the complex dance between Pluto and Neptune. Though now classified as a dwarf planet, Pluto's orbit presents a masterclass in gravitational evasion. Its orbital plane is inclined by 17 degrees relative to the ecliptic plane of the major planets, and its orbit is highly eccentric, meaning its distance from the Sun varies dramatically, causing it to cross inside Neptune's orbit for 20 years out of its 248-year period. Visualize Pluto not as a neat sphere on a track, but as a puck skittering at a sharp angle across an icy rink, its surface a panorama of frozen nitrogen, buffeted by the metaphorical cold winds of the outer system. The reason Pluto has not been consumed or ejected by the far more massive Neptune lies in a precise mathematical relationship known as the 3-to-2 orbital resonance. For every 2 orbits Pluto completes, Neptune completes exactly 3. This resonance is reinforced by orbital dynamics that exploit libration effects, both azimuthal and latitudinal, which ensure that when Pluto swings closest to Neptune, it is always sufficiently distant in angle or significantly offset from Neptune's orbital plane, preventing a physical collision. Cutting-edge research from 2024 has further illuminated this delicate ballet, suggesting that Jupiter played an indirect but pivotal role in maintaining this resonance. Simulations indicate that without Jupiter's massive gravitational influence stabilizing the outer system against perturbations originating perhaps from Uranus, the Pluto-Neptune resonance might have collapsed over cosmological timescales, leading to a catastrophic outcome for Pluto. This near-perfect cosmic choreography evokes a sense of or regarding the subtle balances that permit long-term survival. Expanding our gaze beyond the solar system reveals exoplanetary systems that exhibit orbital architectures far stranger than anything we encounter locally, showcasing planets that have clearly navigated or formed in extreme gravitational environments. Take, for instance, Kepler-166b, a planet orbiting a binary brown dwarf system. Observations published around 2025, utilizing the Very Large Telescope of the European Southern Observatory, confirmed this world possesses an orbit tilted at a near-perfect 90 degrees relative to the equatorial plane of its host stars. Imagine this solitary sphere traversing the void, perpetually bathed in the dim, double twilight cast by 2 fading embers, its journey perpendicular to the plane in which its parents formed. This is the first confirmed polar planet, a configuration that challenges standard core accretion models, suggesting planet formation is far more robust and capable of handling high angular momentum misalignment than previously hypothesized. These worlds didn't just survive, they formed in configurations that defy simple orbital narratives. Another compelling case involves the extreme trans-Neptunian object, 2025VN40, which exhibits an 11-to-1 resonance with Neptune and boasts an orbit so elongated and steeply inclined that its aphelion, the farthest point from the Sun, stretches 140 times the Earth-Sun distance. This object essentially hides in the deep periphery, using its extreme distance as a shield against perturbations from the inner system. Discoveries emerging from surveys like the Legacy Survey of Space and Time underscore the existence of a vast, perhaps dominant, population of distant, resonant, or highly inclined trans-Neptunian objects, worlds whose long, tenuous orbits are themselves a form of successful, protracted evasion. The necessity of shifting orbits becomes even more dramatic when considering the inevitable death throes of a Sun-like star. In several billion years, our Sun will exhaust its core hydrogen and swell into a red giant, engulfing the inner planets. For systems with planets currently in the habitable zone, survival demands a dramatic relocation. Consider the case of 8 Ursae Minoris b, or HALA, a gas giant orbiting a binary system where one component has already evolved into a relatively stable, though expanded, red giant. HALA has managed to endure this stellar transformation, suggesting that its original orbit possessed sufficient stability or eccentricity to avoid immediate engulfment, perhaps by having sufficient semi-major axis separation. One can feel a blend of cosmic terror and speculative hope imagining Earth facing a similar challenge, a theoretical shift away from the expanding stellar envelope. Modeling efforts from space agencies like NASA in 2023 continue to explore gravitational scattering events in aging systems. They suggest that interactions between multiple giant planets can, under specific configurations, slingshot terrestrial worlds outward into wider, cooler orbits, effectively saving them from stellar expansion. Furthermore, the sophisticated mathematical framework underpinning spacecraft navigation, specifically the use of the Interplanetary Transport Network, which exploits the gravitational saddles known as Lagrange points to minimize propellant use, hints at a distant, engineering-based future where humanity might influence planetary trajectories, albeit through artificial means, to dodge impending doom, a concept currently confined to the realm of speculative physics but rooted in observable gravitational dynamics. Recent astronomical observations have focused intensely on objects currently traversing our own system, offering real-time case studies in close-range gravitational interaction. The interstellar object Theia Atlas, detected on an inbound trajectory, is currently under intense scrutiny. Current predictions, refined as of early 2026 observations, suggest a periapsis close enough to Jupiter's gravitational influence, perhaps within the sphere of influence of Jupiter's Hill radius, that it might deposit or capture small, temporary satellites near Jupiter's L4 or L5 Lagrange points, the gravitational balance zones ahead and behind the giant planet. Missions like Juno and the JUICE probe are providing unprecedented data on the subtle gravitational and non-gravitational accelerations acting upon Theia Atlas. While the probability of this object being successfully captured or leaving behind any significant artifact is calculated to be extremely low, below 0.004% based on current trajectory fitting, the very possibility injects a thrilling element of uncertainty into our understanding of interstellar object interaction. We are witnessing, in real time, a celestial body testing the boundaries of our solar system's gravitational hegemony, a miniature drama unfolding that mirrors the larger survival mechanisms we have discussed. To synthesize this sprawling cosmic drama, no planet possesses the agency to consciously select an escape trajectory. However, the myriad mechanisms that govern the formation and evolution of planetary systems, the chaotic yet ultimately structuring forces of planetary migration, the long-term stability afforded by precise orbital resonances, and the ultimate, often brutal, ejection leading to rogue status all serve as natural algorithms for survival against the threat of collision. The universe, in its apparent indifference, demonstrates an extraordinary capacity to favor resilience, where the very energy of gravitational upheaval can sculpt order from chaos. Each surviving planet, Whether it is Pluto maintaining its distant, resonant waltz or a distant exoplanet tucked into a safe, high-inclination orbit, tells an emotional story of successful navigation through the violent currents of cosmic history. Through these detailed scientific lenses, the vastness of space ceases to be merely an empty backdrop. It becomes a dynamic, breathing entity where perpetual motion is the ultimate prerequisite for continued existence. The knowledge gleaned from these distant worlds, from the fiery birth of our moon to the icy solitude of rogue planets, grants us a profound appreciation for the tenuous, yet tenacious, hold life or even mere planetary matter maintains against the infinite, crushing inevitability of celestial mechanics. The next generation of powerful telescopes, such as the planned Large Aperture Synoptic Survey Telescope, are poised to uncover thousands more examples of these evasive maneuvers, further solidifying the fact that in the cosmos, stagnation means obsolescence, and survival is synonymous with ceaseless, complex movement.